Thevenin equivalent example continued. Method 2, independent and dependent sources, a calculational approach. Method 1 cannot be applied if dependent sources are in the subcircuit. Only method 2 is applicable. The process for method 2 is step 1, determine VOC, which is the same as VTH. And then on step 2, here's where they differ now. You place a short across the open AB and calculate IAB, which is the same as I short circuit, which is the same as I Norton. And then step 3, we determine RTH by the ratio of VOC divided by I short circuit. So let's do it. So step 1. Determine VOC, which is the same as VTH. Now note, we've already done this already. We did it in method 1, so what I'm going to do here is that I'm going to take it from method 1 and just put it in. So once again, we've already calculated VOC in method 1, which is exactly the same thing. So what I'm going to do is transfer that information here. So if I place my circuit here, this is what we did. This is what we did in our previous method. So we're done with VLC. So now what we have to do is go on to step 2. Here, we need to determine I short circuit, which is the Norton current. So with all sources active, place a short across nodes A to B. The sign convention for current flows from node A to node B. So this is a sign convention, so we have to follow that sign convention. So let me paste that. And then here's my circuit here. So now I'm going to place a short, and the whole goal is to calculate this current, which is I short circuit between these two nodes. Again, look at the sign convention. It doesn't go from B to A, it goes from A to B. Question. Which technique will you use to determine I short circuit? I would say that don't ponder on this choice too much, since most students will always, well, I should say, will almost always go to their strongest, skill. So in other words, if you really like mesh analysis, then you're going to go after mesh analysis. If you're going to use node analysis, you're going to go to node analysis. If you're going to do simple circuits, then you're going to go to simple circuits. So what we should do here is that we should look at a couple of these guys. And one choice that we can do is that so if I look at that, probably the popular ones, of course, is loop analysis. So if I look at loop analysis, what do I see here? So if I bring my circuit down here, and I paste it right up here. So here's my circuit right here. So I have my short. And the obvious choice for most people would be, yeah, let's use loop analysis to calculate that current I short circuit. So let's pick our current. So we should pick this guy as I short circuit. I'm going to pick this one. I'm going to call this IX. And then I'll pick this current right here as IY. So if I do the counting, then I have 3 loops, which tells me I have loop for I short circuit, the loop for IX, and of course the loop for IY. So if I look at this, I now have set up 3 equations and 3 unknowns. So this is what we end up with. But what if we looked at node analysis? So if I look at node analysis, I could come in and place my circuit again here. And if I look at this circuit, the first thing that I note is I'm going to choose my ground, and a good choice for the ground, at least in my mind, is right here. Now remember, that ground goes all the way up here because that's a short. So if I choose this to be the ground, this is also the ground right here. So when I look at these nodes, we know this node has to be 18 volts. And then I have this middle node, which I will then call, let's say, Vx. So when I look at this, I see that I only have one node, right? I have two nodes, but I know one of them. So if I was to do this the right way, I would say I have two nodes minus one source. So I have one node. And that node is, of course, Vx. But then I look at I short circuit. That's what we want to do. And I would come in with a solver equation for I short circuit. So in this, I have two equations and two unknowns for Vx and I short circuit. So what am I going to do? I'm going to do node, since most of you already picked loop. So let's do that. So I pick node analysis to determine I short circuit. So let's write it out. So the first thing I need to do is that I see that my node Vx, I have three resistors connected. So I'm going to have 1/6, 1/3, and 1/10. And that's going to be Vx. Now I'm going to look at mutuals. And you could see that the 10 and the 3 are connected to the ground. Only the 18 survives. So now, because I get a minus sign, I'm going to take it to the other side. And this will give me 1/6 times 18. So right away, I can solve for Vx. Right? There's only one equation and one unknown. And this gives me 5 volts. So I now know what that node voltage is. So the next thing here is to apply KCL as a solver to determine I short circuit. So I'm moving this up so that I can actually write it right here. So when I look at that solver, I have to apply KCL at node right here, node A, because there's I short circuit. I know that voltage. I know that voltage. So now I'm going to apply KCL. So my solver equation for I short circuit, that tells me that apply KCL at node A. So then if I do that, I'm going to see that I'm going to have I12. I'm going to assume here that the currents are going this way, which they are. So then I12 plus I10 has to equal I short circuit. So this has to equal I short circuit. So then that tells me then I short circuit is then going to be the 12, which will give me 18 minus 0 divided by 12. And then I'm going to get 5 minus 0 divided by 10. And if I compute that number, I get that I have 2 amps. So now I have I short circuit. So then I just move on to step 3. So step 3 says determine RA, excuse me, RAB, which is the same as the Thevenin resistance. So if I look at the ratio here, we then see that RAB, which is RTH, is going to be VOC divided by I short circuit. We already calculated that this was 12 volts. Now this is 2 amps, and I get 6 ohms for RTH. This is the exact same solution that we derived using method 1. They truly are the same. So in summary, the Thevenin Norton parameters from the viewpoint of the load have effective values of VTH equals to 12 volts, I short circuit, which is 2 amps, and RTH, which is the same as R Norton, which is 6 ohms. They see/feel the same values at the open.